All right, good morning, guys. So I had intentions of uploading this at 8 from last semester. However, I cannot find this video. So I'm going to make a new one really quick, and I will get this out to you ASAP. And it will be on the YouTube channel. I'll send you the link. All you have to do is click it, and it takes you exactly to the video. Okay? So you should be on Agile Mind. And remember, today we are doing Topic 1, SAS 2, in pages 7 through 13 in our workbook. So we are starting on page 7, number 1. All right, and so remember yesterday we talked about these triangles. So this right here on the screen showed us that this was a linear function. That is because each time the perimeter increased by a constant rate, a constant addition of 1 unit. Okay? We know that if it's adding the same thing every time, that is an arithmetic sequence. All right, so right here it tells us you can represent this arithmetic sequence using function notation. All right, so how this works, it's called a recursive definition. And all it is the term is defined using the term before it. So in order, let's say we want to find out term 7. Well, in order to know term 7, we must know term 6. If we want to know term 42, we must know term 41, okay? So we have to know all the terms before it to answer that term it's asking for. So for this specific problem, number 1, it gives us this information. It says that f of 1 equals 3. So that means when I put in a 1, I get out a 3, okay? F of 2 would be 4. F of 3 would be 5. F of 4 would be 6. Now, however, okay, so we know f of 1 equals 3. We are given a function rule right here. F of n equals f of n minus 1 plus 1. All right, that n minus 1 right here is the recursive definition, okay? So the question is, for this sequence, what is f of 5? What does f of 5 mean in the context of the situation? Okay, you can look at the pattern, obviously, and know that f of 5 equals 7. You know that because you can look at the pattern. But we have to show how that works, okay? So, recursive definition. You look for the term before what you're looking for. So, we are looking for f of 5. That's what it tells us right here. Equals f of n minus 1 plus 1. Well, 5 is our n, so we just plug it in. F of 5 minus 1 plus 1. Now, all you do is simplify. You say f 5 minus 1. Well, 5 minus 1 is 4 plus 1. Now, here's where you have to go back and use the term before. What did we say that f of 4 was? F of 4 equaled 6. So, we say 6 plus 1 equals 7. So, f of 5 equals 7. Okay? Now, if you hit check, it should show you that answer in that work that we did. Okay? So let's go ahead, hit our green arrow, and it goes ahead and jumps to 3 and 4. That is because number 2 is a reinforced problem. So I am going to go to a different screen, and we are going to work through some of these. We're going to do A and B on here, and then when you come to class tomorrow, we will do C, D, and E together in class because they're a little bit different, and I want to be able to teach you those in class, okay? So let's just start out with number 2A. So it tells us to find the first 4 terms of a sequence using the recursive definition, okay? So we are going to start with the first one. So it tells us that f of 1 equals 6. So that means when we plug in a 1 to our equation, we get out the number 6, okay? So the equation, though, that we are given is f of n equals f of n minus 1 minus 5. Now, it tells us again that integer values of n are greater than 1. So that means we have to start with numbers greater than 1. Well, it tells us to do the first 4 terms. So obviously we're going to find term 1, term 2, term 3, and term 4. But we are already given term 1. So we only have to find 3 terms. Okay? So what we're going to do first is we're looking for f of 2. Okay? Equals f of 2 minus 1 minus 5. So the number in your parentheses, that f of, that is your n every time. So now we just simplify. F 2 minus 1 is 1 minus 5. Well, then you have to go back over here to the previous term, right here, and say, well, f of 1 was 6, and 6 minus 5 equals 1, okay? So now we know that f of 2 equals 1. Now we keep the process going. So we found 2, so now we can do 3. So f of 3 equals f of 3 minus 1 minus 5. Remember that f of, that of number, is the n. So we just simplify. 3 minus 1 is 2. Bring down that minus 5. Well, now we have to look. Well, f of 2 was 1. So we say 1 minus 5 equals negative 4. So now we know that f of 3 equals negative 4. And then we find the last term, which will be f of 4. So we're using this function rule every time, in case you haven't noticed. So we've got f of 4 minus 1 minus 5. So f of 3 minus 5. Well, f of 3 was a negative 4. So we have negative 4 minus 5, which equals a negative 9. So we have a set of numbers 6, 1, negative 4, and negative 9 are the first 4 terms for this function notation using the recursive definition. Okay? All right, next, B tells us that f of 0 equals 8. The function notation is f of n equals 2 times f of n minus 1 plus 6. So here we are doing the exact same thing, okay? We are given f of 0 equals 8. All right, so now we've got to find the first 4 terms. So we've got to find f of 1, f of 2, f of 3, and f of 4. So we are going to start by finding f of 1. So we've got 2 times f of 1 minus 1 plus 6. All right, we simplify. 2 times f of 0 plus 6. All I did was subtract 1 minus 1. Now we have to look back. What was f of 0? Well, f of 0 was 8. So we say 2 times 8 plus 6. 2 times 8 is 16 plus 6 more will be 22. Okay, so now we know f of 1 equals 22. All right, so let's do the same thing, except this time we will do f of 2. So we put our function rule. We simplify. 2 minus 1 is 1. Well, now you have to look back. F of 1 was 22. So we're saying 2 times 22 plus 6, which equals 50. So f of 2 equals 50. Okay? All right. Next, we're doing the last one, f of 3. So use our function rule. We have to look back and see what f of 2 was. Well, f of 2 was 50. 2 times 50 is 100 plus 6 is 106. So f of 3 equals 106. So now we have a set of numbers: 8, 22, 50, and 106. Okay? All right, so remember, we're going to do C, D, and E in class, so you can leave those blank until tomorrow. All right, now, you should go back, or you should be on your Agile Mind, and we're going to be able to answer 3 and 4 using this page. So it says on your screen, you have seen how an arithmetic sequence can model a geometric problem, which is what we just did using that recursive definition. Now, consider a different situation. Amanda is a part of a committee considering the design for remodeling her school's auditorium. One design the committee is considering has the seats staggered so that no one's view will be blocked by the person sitting in front. Play the animation and see how this might look. All right, so it tells us right here in blue. The first row has 20 seats, and each row has 3 more seats than the row in front. I'm going to play this animation. All right, and it says, how can you use the pattern you see in the first 3 rows to determine how many seats will be in each row? Well, what does it tell us? It tells us that first term, okay, that first term is 20. And we are going to be adding 3 more seats to the row in front of it, okay? So let's click here. Yeah. Go ahead and click that next green arrow, and it's going to pull up that table on number 3. All right, so on your screen it says use the pattern of constant differences in the table to develop a rule that gives you the number of seats. All right, so on your chart, I want you to jot down that we are adding 3 each time. So that makes our common difference equal 3. All right, so I want you to take just a second and fill in your chart. All right, now you can hit check on your screen. We started with 20, add 3, 23, add 3 more, 26, add 3 more, 29, add 3 more, 32, and add 3 more, 35. Okay, easy enough, right? All right, now let's answer number 4. It says, what kind of function can be used to model the data in the table above? Justify your answer. Okay. So, there are 2 different ways that we can do this. I want to show you both ways. So, the first way, which is mostly how you will see this, and it includes y equals, this is for number 4, the first term plus the common difference times n minus 1. Okay? So we have to look. Y equals, what is the first term? 20. Plus our common difference. What did we write the common difference was? What is it doing every time? It's adding 3. And that recursive definition, we just bring it down, n minus 1. Okay? Here's why it works. If I am looking for row 5, okay? Looking for row 5. I'm going to have to move over here to this side. I'm going to plug in 5 for that n. So, y equals 20 plus 3 times 5 minus 1. 20 plus 3 times 4. 20 plus 12 is 32. Does that match? Yes. That is why that works. So, what you need to take away from this specific slide is this right here. I want you to put a box around that. Very important to know for arithmetic sequence. All right. Another one we can use is let's work backwards, okay? We started with we started with figure 1, all right? Let's go to 0. How many seats would 0 have? If we are adding 3 every time. Remember, if we work backwards, we change the operation. So now we would say 20 minus 3 and get 17. So another example you could write this would be y equals 17 plus 3x, or y equals 3x plus 17, okay? These two are in slope-intercept form. Okay? Now, same thing. If you plugged in a 1 for that x, we should get out 20. So y equals 3 times 1 plus 17. Well, 3 times 1 is 3. 3 plus 17 is 20. So that one also works. Okay? All right, let's move to the next screen. We can answer number 5 here. It says, what kind of sequence is generated by the number of seats? How do you know? So I'm going to go ahead and click this animation. And you can already answer this without even having this animation. You know that it is an arithmetic sequence because it has a common difference of 3. Meaning it adds 3 every time, okay? It has that rate of change, that constant addition, whatever you want to call it. All right, let's see. All right, so this screen is just a checkpoint, kind of. So it says, study this arithmetic sequence. The first term is denoted as T1, and you know the first term is 20. All right, it says the sixth term is 35. What is T4? All right, so all you're doing is you're going here looking for the 4, and you know that it is 29. If you hit check, it will tell you it is 29. Okay? Now, it goes on to say, you know that each term in the sequence is 3 more than the previous term. Formally, if Tn represents the nth term of the sequence, then Tn minus 1 represents the term previous in the sequence. So all it is using that function notation that we did on number 2. Nothing is changing. You just have to know that if you see that n minus 1, you have to know all of the terms that comes before it. So like it says, if I want to find the 100th term of the sequence, then we are going to need to find every one of the first 99 terms before we can find that 100th term. Okay? All right, number 6 is just asking us to write that recursive definition to demonstrate this sequence. So remember what I said. Y equals the first term plus the common difference and n minus 1. Okay, so again, y equals 20 plus 3 n minus 1. All right, so that's the first part of the problem, and if you hit check, it will show you that. They use Tn, remember, same thing as y. Okay, nothing changes. They're just using different letters. No big deal. All right, so now it wants to know how many seats will it be in the 21st row. All right, so 21 is our n. So we're looking for f of 21. So 20 plus 3, 21 minus 1. 20 plus 3, well, 21 minus 1 is 20. So 20 plus 60 equals 80. So the 21st term would be 80, and it shows you that exact thing right there. Okay? Now, the last part, remember I showed you a second ago about the slope-intercept form, y equals mx plus b. All right, that 3x plus 17, how is that the same? Well, in the slope-intercept form, y equals 3x plus 17. What's my slope? Well, my slope is 3, also known as the rate of change. But in my first equation, y equals 20 plus 3 is my common difference. So what it's trying to show you here is that the common difference and the rate of change are the same in both equations. They are both equal to 3. Okay? And it says it right here on the next page. The common difference D of the sequence will be the same as the rate of change or slope m in the linear function. Okay, so just jot that down somewhere on number 6. All right, on number 7, we're actually going to skip number 7. So on your workbook page, I want you to mark out number 7. Mark out number 7. All right, now number 8 is a reinforce. So we are giving -5, 1, 7, 13, 19, and 25. So before we start, we need to see what the common difference is, okay? So from -5 to 1, what do we have to do? We have to add 6. Is 1 plus 6, 7? Yes. 7 plus 6, 13. 13 plus 6 is 19, and 19 plus 6 is 25. So we've got to write 2 equations. So I'm just going to jot down that the common difference is 6. So we've got 2 equations. Let's do the easy one first. Remember, y equals first term plus common difference n minus 1. Y equals, the first term is -5 plus 6, which is our common difference, times n minus 1. Okay? The second would be that recursive. So we have, you can do a to the n. Let's just stick with y. Y equals a to the n minus 1, and then plus your common difference. So remember, this right here means we have to use the previous term in order to know the current term we're looking for. And we'll talk more about that in class on Friday when you're back here. All right, so let's look at number 9. So it says, but why use an arithmetic sequence when linear functions will provide similar information? Return to the auditorium situation for a moment. Suppose the auditorium is to have 12 rows. What is the total seating capacity of the auditorium? Adding the seats in rows 1 through 12 is the same as finding the sum. Remember, sum is when you add everything together. Of the first 12 terms of the arithmetic sequence that represents the number of seats in each row. All right, it's just showing you the seats, how it adds 3 every time. Okay, so I want you to jot that part down. It says each row has 3 more seats than the one in front of it. So each term in the sequence is 3 more than the term before it. Yes, we know that. All right, look at the pairs of terms. So you see what they did. They took the first term and the last term, and they got 73. Now they're going to take the second and the 11th term and get 73. They're going to take the third and the 10th, the 4th and the 9th, the 5th and the 8th, and the 6th and the 7th. So look, they are seeing how many pairs of 73s they get. All right, well, if you have 12 terms altogether and you're looking for the pairs, well, a pair means 2. So can't you just say 12 divided by 2 and get 6, which is what they got here. 6 pairs to 73. So guess what you do next? You can take 73 and you can multiply it by 6 to get your sum, which is a total of 438 seats. All right, for number 10, this is where you want to drag and drop your things to get credit on Agile Mind. Now suppose that Amanda's committee is considering adding auditorium plan in which the first row of seats will have 15. All right, what does it tell us right there? The first row will have 15. So we can go ahead and drag 15 to our T1. Okay, now you're going to want to write this down on number 10 as we go. And each row will have 5 more seats than the row in front of it. All right, well, that D is standing for the difference. So what does it tell us? It will have 5 more seats in each row. Like the first plan, the number of seats in each row, this also forms an arithmetic sequence. Can you solve this puzzle to explore the second plan? All right. Remember, first term plus the common difference times n minus 1. So the first term is 15. The common difference is 5. And we have to use that recursive of n minus 1. Okay? Now, it asks us to find t of 18. So, we've got to use this function rule. We're looking for T18 equals 15 plus 5 times 18 minus 1. 15 plus 5 times 17. Well, 15 plus 5 times 17 equals 100. Okay? So now we drag and drop 100 right here. Okay? All right, so now let's just jot down a couple things. We're looking for the first term, which was 15, and the last term, which is 100. Okay, now It's looking for S of 18. That means the sum, okay? So remember, to find the sum, the easy way, we want to take the first term plus the last term, and we get 115. This is what we did on number 9, just a new set of numbers. So we've got 115. Now, we have to look for the number of pairs. If we have a total number of 18 rows, how many pairs will I have? Well, 18 divided by 2 is 9. So now, all I do is I say 115 times 9, and I get 1,035 seats. So that means if I took the time to work out this problem for everything and then added all of those numbers up, I would get 1,035. This is just the short and simple and quick way. All right, so now we're going to drag and drop this, hit submit, and it should tell you good job. All right, this just shows you what we just did again. So let's go ahead and skip this one. All right, go ahead and mark out number 11 on your workbook. Number 11 we will not do as well. That goes with number 11, so we will not do this one. All right, so let's look here at 12, 13, and 14. All right, so if a series contains many terms, writing each term can be very tedious. For this reason, mathematicians have developed a shorthand notation to indicate a series. This notation makes use of the Greek capital letter sigma. So that fancy E is a sigma, to stand for the sum, as well as the formula of the nth term of the series. The notation is often referred to as the sigma or the summation notation. All right, so somewhere on your paper, I want you to write the sigma equals a sigma or summation, and then I want you to put sum in parentheses. Okay. All right. I'm going to hit play. All right, this is what this means. Number 12, it says write the series represented by the sigma notation. So we are expanding this series, okay? So you're given this fancy sigma and this notation and all this. All right, well, this n minus 1 right here, or n equals 1, sorry. It tells you n equals 1. You were going to start with 1. The 5 up here is the number of terms you are looking for, okay? So, if that said 10, you would be looking for 1 through 10. Got it? All right, so now all you do is plug in the numbers. So I'm going to go ahead and hit play, or hit 2 for me, and it'll show you when you plug in a 1, you get out a 5. You plug in a 2, you get out an 8. You plug in a 3, you get out an 11. You plug in a 4, you get out a 14. And you plug in a 5, and you get out a 17. Now, look at those numbers. They are increasing by what every time? They are increasing by 3 every single time. Got it? That's all that means. So, now, on number 13, it says represent the series 20, 23, 26, and so on. Basically just adding 3 using the sigma notation. Okay? So I'm going to hit play. And the first thing I want you to write down is the sigma. Okay? Up top is the number of terms that you're given. How many terms are you given? Count those terms for me right now. You are given 12. Okay? Now, n equals 1. That means you plug in a 1, you get out a 20. You plug in a 2, you're going to get out a 23. Okay? So now we have to determine the function rule. This is an arithmetic sequence, the same one we've been doing all day. So we have 20, first term, plus the common difference times n minus 1. Okay? That's what that means. So let's hit the 4 and see what it shows us. Shows us the exact same thing we did. Okay? All right, let's move to 14. Drag the tiles to represent the series. So make sure you have this written on your paper. All right, so up top, it's the number of terms you are given. Down here, you are starting with the first term. Then you have the common difference, n minus 1. This right here more than likely will always be 1. Okay? So, how many terms you got up top? 14. N equals 1. The first term is 15. The common difference, they are adding 5 every time. And minus 1. Okay? Now, if you flip over to number 15, it's a reinforce, and I want you to do that one on your own. Okay? All right, I hope this video helped. Sorry I'm late getting it uploaded. See you tomorrow when we will come in, do a little review from today, and start SAS 3. Have a great day.